Now let us take another very important element, which is the transformer. We have just two more elements left, the transformer and the gyrator. Okay, then we complete all the 9 elements of bond graph. So coming to transformer, it's a two-port element. That means the transformer can be represented like this. There are two ports, 1 and 2. Okay. And there is a modulus associated with this transformer. We have indicated that modulus as mu. You have effort 1 and flow 1 associated with bond 1. Effort 2 and flow 2 associated with bond 2. Now the relationship, what a transformer does, it converts flow to flow or effort to effort. Okay. So flow 2 is equal to mu times flow 1. Okay, this is the relationship which the transformer makes use of. Flow 2 is equal to mu times flow 1. But the transformer as such is a device which just whatever power comes in, it lets that power to go out. It doesn't store or destroy power. Okay, so it's a power conserving transformer. And so E1 F1, which is the input power, has to be equal to the output power, that is E2 F2. Now you can write F2 as mu times F1. And when you compare these two left and right sides, you can see that you can arrange it like this. E2 into mu into F1. Left hand side, left hand side and right hand side, if you compare, you see that effort 1 is equal to mu 2 is a relationship which automatically emerges out if this relationship is to be held always. Okay. So while you specified in the beginning only one relationship between flows, flow 2 is equal to mu times flow 1. The property of the transformer is such that the other relationship automatically emerges out. Effort 1 is equal to mu times effort 2. Okay, and it happens because of the power conserving nature of the transformer element. So please remember this, F2 equal to mu times F1, E1 equal to mu times E2. Okay, this is how a transformer functions. Let us take an example of gears in mesh. Spur gears in mesh. So we have two spur gears. The gear is of teeth N1, number of teeth N1, and the pinion has N2 number of teeth. Let's assume that counterclockwise sense of rotation is positive, and we have angular velocity omega 1 and tau 1 are the angular velocity and torque associated with the shaft, gear shaft. And angular velocity omega 2, tau 2 are the, of course, this is indicating the convention. It's not that actually it rotates in this direction when this gear, it's just showing the positive convention. Now we know that omega 2 is equal to minus n1 omega 1 upon n2. I hope you agree to that. All of you know about this relationship, so I'm not going into the depth of this. I hope all of you know this relationship.
Yes, sir.
Yeah. So omega 2, that is the angular velocity of the pinion, is directly related to the angular velocity of the gear by the ratio of the number of teeth. And of course, this minus sign is because the direction gets reversed. Okay, when you have simple spur gearing like this, automatically you see omega 2, that is relationship between flows, is minus n1 by n2 times omega 1. automatically you get the relationship between efforts, that is tau 1 is equal to minus n1 by n2 times tau 2. Okay, so this is a relationship which emerges out automatically. So you can boost torque. The angular velocity will drop, but you can boost torque, okay, by using a pinion gear system like this. So even with a small torque, you can develop a higher torque at the output shaft of the gear. Okay? So a small torque applied at the pinion. So this automatically, this represents the relationship for a transformer. We also have other examples of the transformer like the hydraulic cylinder, where we have two distinct domains, energy domains. So you have the mechanical energy domain, that is force and velocity. These are the components, these are the variables of power associated with the mechanical component. Here you have a piston and this is a chamber, and this fluid here in this chamber, which is coming out at the rate of Q. Volume flow rate is Q. And the pressure that is maintained over here is P. Pressure that is developed is P. Let's assume that the area of cross section of this piston is A. Okay, normal to this pressure. And you can represent the mechanical side as F using this bond with the power variables F, that is effort, and V, that is the flow. So force and the velocity with which it is moving. So this is actually the mechanical power that you're inputting on this piston. On the fluid side, you have the variables of power P and Q. Okay. Now, what is the relationship between F and P and V and Q? Can you tell me? We can represent this relationship because it's a flow to flow relationship or effort to effort relationship. We can use a transformer to represent this relationship. We can write Q, that is the volume flow rate, as A multiplied by the velocity of this piston. So the rate at which fluid is coming out is equal to A multiplied by V. Okay. Automatically, because it's a transformer relationship, you get force is
Excuse
equal
me,
to
sir.
A into P. Yes. Yes, please
Sir,
go
can you
ahead.
please explain this again? Sir, can you please explain this again?
What is it that you did not understand? Can you tell
Sir,
me?
how we how we use the transformer here?
Yeah, so that's what I'm explaining right now. You see, there is a relationship between Q and V. Okay, and between F and P. So you can use this transformer with modulus A. Now, what is the relationship? Q is equal to A multiplied by V. Okay, so here you can see that you can see that Q, this Q is equal to A multiplied by V. Okay, the volume flow rate at the time T. This is as simple as this relationship between two flows. Okay, so here you had flow 1 and this is flow 2 and this is effort 1 and this is effort 2. Okay, so what you got is flow 2 is equal to mu times flow 1. Okay, This relationship, I'm sure you already know. So I think there is no point in discussing it. If you're not clear about it, I can explain it to you. Do you have any doubt on this?
No, sir.
Okay. So actually it is the volume flow rate. Volume flow rate is equal to A multiplied by V. Okay. So in fact, if you want to elaborate, you can also look at it like this. Suppose that in time, let's say that in time, there is a little movement of this piston. Okay. Let us say that this piston has moved from here to here. Okay. And this displacement is delta x. Okay. So naturally, when this moves by delta x, what is the velocity? The velocity is in the limit delta t tending to 0, delta x by delta t. Do you agree? The rate at which this piston displaces with respect to time. This is the classical definition of velocity. Agreed? Now
Yes,
what
sir.
we are doing
Yes, sir.
Yes,
is
sir.
now we are going to work out what will be the volume of fluid that is going to be displaced when this piston moves from here to here. What is the volume? It is this area multiplied by this distance which it has moved.
Delta
Okay.
X.
Yeah.
ADX.
So the volume flow rate will be what? It will be the volume. Volume is what? Delta X multiplied
Into
by A. Okay. And because it's the flow rate, you have to take the rate of the flow. So this is with respect to divided with respect to time.
time.
Now what you observe here is this is actually just the velocity, this part. It's just velocity. So you are left with Q is equal to A into V. Q is equal to A into V. Okay. I hope now it's clear to you how we got this modulus A.
Yes, sir.
Okay. So in the process, you also find, which you are already familiar with, that force is equal to A multiplied by the pressure. Okay, area multiplied by this pressure will give you the force. Okay, so that's also known to you. And that relationship automatically emerges out. This relationship between force and between pressure at the time t. Okay, this relationship is directly uh, just mu multiplied by effort. Okay, so it is just effort 1 is equal to mu into effort. So that's it. As far as the causality of the transformer is concerned, uh, we can consider a transformer like this. And because the transformer is just a flow to flow or effort to effort, you can have causality like this. So flow 2 is equal to mu times flow 1. So it's a relationship between flows. So if you provide flow as input, flow as input, flow should be available as output. So naturally, the causal stroke will come like this. So flow being provided as input, flow will be produced as output. If you look at it from the other side, you can see effort 2, if it is input, then it will produce effort 1 as the output, which is visible in this relationship. So you can also represent the transformer causality like this, where you have the input is effort 1 and output is effort 2. So in that case, the stroke will come like this. And flow, the relationship between flow 1 is equal to 1 by mu times flow 2. Okay. So essentially it is just flow 2 is equal to mu times flow 1. But because of the causality, the way in which causality is written, you have this equation. The equation is the same, but the way it is arranged, what is the input, what is the output? Okay. So I think we will cover the gyrator, which is the last element in our next lecture. That is tomorrow.